Hello everyone. Today we will be talking about smart pointers and RAII. It is one of the most useful features of modern C++. It is an idea that makes our code more safe without making them more complicated. In fact, once you get used to with this idea, you will probably wonder why didn't we even learn this earlier? Up to this point in this course, we've worked with dynamic memory management using the new keyword and delete keyword. We also spent time talking about copy constructors, destructors, move semantics, and exception safety. Those topics might have felt like separate pieces, but today they will all come together. The goal today is not just to learn another library. It is to understand a programming style in C++ that everyone talks about and C++ itself encourages. So, before we talk about smart pointers, I want you to think about a simple function. Imagine we have a function that takes a book object. It checks whether the book belongs to a certain genre or not. And maybe it also checks its rating, and then it prints a recommendation or returns some information. At first glance, that sounds like a very ordinary function. You read it from the first line to the last line, and everything seems straightforward. But here's the interesting question. Does the program always execute every line from top to bottom? The answer is no. A program can leave a function early, it can skip a block of code, even worse, execution can suddenly stop because of an exception is thrown. Today we are going to look at something called code paths, and once you start thinking this way, you'll understand why exception safety and automatic resource management are so important. So what exactly is a code path? A code path is simply one possible route the program takes while executing a function. Think about driving to campus. You have one destination, but there might be several different routes depending on traffic or road closure. Programs work the same way. Whenever there's an if statement, a loop, a function call, or an exception, execution may follow different routes. The important thing is that when we write code, we shouldn't only think about the only happy path that the code takes where everything works perfectly. We should also have to think about every other possible paths. What happens if a condition is false? What happens if memory allocation fails? What happens if another function throws an exception? Those are all different execution paths that our code has to handle correctly. So the question on this slide is simple. How many different paths the function can actually take? At first, if you are like me, you will underestimate the answer. So let's count the path that we can see here. So here our function contains one if statement. Inside that if, the program checks whether the book genre is fantasy or not. If it is fantasy, then we take one path. If it isn't fantasy, another condition checks whether the rating is high or not. So then we go through that another path. And finally, if both of them are false, then the whole if block is skipped. So from what we can actually see here, we have three possible execution paths. That's a perfectly reasonable answer if you say it's three. In fact, it's exactly the answer many of us would give after reading the function for the first time. But C++ likes to hide some surprises. Those three paths are the visible ones. There are many more that are much harder to notice. So here, as you can see from the slide, things have become much more interesting. The function doesn't only have those three visible paths, it also contains many hidden places where execution could suddenly stop. Every function call might throw an exception, every memory allocation might fail, even operations that look completely harmless may internally perform work that can fail. When we count all of those possibilities, this small function suddenly has at least 18 additional error paths. So that's a huge jump. Just because they are error paths doesn't mean they are not code paths. They are also the code paths. Three visible paths suddenly become more than 20 possible execution paths. So the important lesson here is not actually the number. The important lesson is that C++ programs are often much more complicated than they first appear. If our resource cleanup depends on reaching one specific line of code, then every one of these hidden paths become a potential bug. Now we are going to uncover where those hidden paths come from. Let's start before the function body even begins. Suppose our function takes a book object by value. That means C++ has to make a copy of the original object before entering the function. Now, think back to our previous lectures. If book owns dynamic memory, then its copy constructor probably allocates new memory. Memory allocation can fail. If that happens, the copy constructor throws an exception. So the exception happens before the first line inside the function ever runs. That's easy to forget because when we read the source code, we naturally start at the opening brace. The compiler doesn't, of course. It first has to prepare the function's parameters. If something goes wrong there, execution never even reaches our function body. So we have already found another hidden code path, and we haven't looked at a single line inside the function yet. Let's step into the function itself. Imagine we call b.genre. At first glance, it feels like we're just reading some data from the object, but genre is still a function call. So function can throw exceptions. Maybe the genre information hasn't been loaded yet. Maybe the underlying data is missing. Maybe the object is in an invalid state. All of those are design choices made by whoever wrote the book class. Suppose genre returns a standard string. Creating or copying that string may require allocating memory. That allocation can also fail. Then we compare it with the string fantasy. Even that comparison involves function call and temporary objects. So what looked like one simple condition actually hides several different places where execution could stop unexpectedly. Then the same idea applies to the rest of the function. We have b.rating. Then later we call title and author. Each function call creates another possible execution path. Each one has the potential to change the control flow completely if any one of them throws an exception. Now let's look at something that surprises many people: printing to the console. We often write something like this. Most of us treat that as if it can never fail. But remember, that operator is just another function. In C++, operators are often overloaded. That means that operator isn't magic, it's an ordinary function call with a special syntax. Under certain circumstances, stream operations can throw exceptions. It doesn't happen often, but it can happen. The important point is that even code that looks completely harmless may still introduce another hidden execution path. Now let's look at the return statement. Behind the scenes, C++ breaks this into several separate operations. First, it gets the title, then it creates a temporary string, then it appends by, then it retrieves the author, and then it creates another string containing the final result. Each concatenation may allocate memory. Each allocation is another place where an exception might occur. The compiler hides all of that work for us, which makes the code easier to read. But the hidden work is still happening. Now let's put everything together. The copy constructor might throw, genre might throw, constructing temporary string from genre might throw, comparing strings might throw, rating, title, author, those can throw. Every stream insertion operation is another possible failure point. String concatenation introduces several more opportunities for memory allocation to fail. And when we add everything together, we end up with at least 18 hidden error paths. Once again, don't focus too much on the exact number. If someone counted 19 instead of 18 because of a library implementation, that isn't the important part. There are far more execution paths than the source code suggests. Now, let's connect this entire discussion with dynamic memory. Suppose at the top of our function, we allocate some memory like this, and at the end of the function, we also delete the object like this. That seems perfectly reasonable. We acquire the resource, we release the resource. But the problem is everything in between. Remember those 18 paths that we just talked about? If any of them throws an exception before we even reach delete, the cleanup code is skipped. The pointer disappears, the allocated memory stays behind, and that's a memory leak. Notice how fragile this design is. New acquires memory from the heap, and delete gives that memory back. Between those statements, our program is vulnerable. Every function call, every allocation, every operation that might throw, all of them create opportunities for execution to leave the function early. If that happens, delete never runs. This is why many of the C++ programmers become nervous whenever they see a raw new. The problem isn't the keyword itself. The problem is the responsibility it creates. Once you acquire a resource manually, you are also responsible for releasing it correctly along every possible execution path. What exactly is a memory leak? A memory leak happens when a program allocates memory but never releases it. That unused memory remains reserved until the program finishes. For a tiny program that runs for 1 second, you might never notice. But imagine a web server that's running for weeks, or a game engine that's running for hours, or a database server that handles thousands of requests, or an autopilot system of an airplane where hundreds of lives are dependent on your C++ code. Even small leaks accumulate over time. Eventually, the program consumes more and more memory, performance drops, the operating system starts working harder. In the worst case, the program may crash because it runs out of available memory. So if cleanup depends on reaching one specific line of code, then the program is fragile. So the point I'm trying to make is if you allocate some memory and forget about it, or somehow your program accumulates it, it's gonna stay there. And it's just like the meme. Why shouldn't it keep it? You told the program to keep that memory, to allocate that memory, and it's gonna pile up and it's gonna drop your performance eventually. Memory isn't the only resource that behaves this way. Think about opening a file. You have to close it. Think about locking a mutex. You have to unlock it. Think about opening a network socket. You have to close that as well. The pattern keeps repeating. So first we acquire a resource, later we must release it. The problem is always the same. What if something goes wrong before we reach the release step? This is much bigger than memory management. It's really a resource management problem. So let's talk about the solution. Think back to our example with new and delete. The issue wasn't that the new keyword is bad. The issue was that cleanup depended on us reaching one specific line of code. If an exception interrupted execution, that cleanup never happened. So what do we actually want? We want memory management to be automatic. We want it to work correctly even if exceptions occur. And we want the lifetime of the memory to match the lifetime of the object that owns it. So in other words, if an object owns some memory, then that object should also be responsible for releasing it. Nobody outside the object should have to remember to call delete. That simple idea is one of the foundations of modern C++. So, what is RAII? RAII stands for Resource Acquisition is Initialization. I'll be honest, the name isn't very intuitive at first when you hear it. Don't worry if it sounds a little strange. Instead of memorizing the words, focus on the idea. Whenever an object is created, it acquires the resources it needs. That resource might be heap memory, it might be an open file, it could even be a network socket or a mutex lock. From that point on, the object is responsible for managing that resource. Then when the object is destroyed, it automatically releases that resource. That's the whole idea. Acquire when the object is created, release when the object is destroyed. Once you understand that sentence, you've understood the heart of RAII. Resource acquisition is initialization. RAII is a programming principle we use throughout C++. The rule, once again, is very simple. If a class owns a resource, it should acquire that resource in its constructor. Then it should release that resource in its destructor. Why is that useful? Because destructors are called automatically. When an object goes out of scope, C++ destroys it. It doesn't matter whether the scope ends normally or because an exception is being propagated. Either way, the destructor runs. That means cleanup happens automatically. This is different from writing just the delete keyword at the bottom of a function. With RAII, cleanup is tied to the object's lifetime, not to a particular line of code. That small change makes programs much more reliable. It's one of the reasons C++ has such powerful resource management compared to other languages. When we write a normal function and when we write an object, create a class, it's totally different. So I wanted to leave this quote behind because I think it's both funny and reassuring. He is Björn Straustrom, the creator of C++. He once said this in an interview because he himself is not that proud of the naming. Resource acquisition is initialization. And I think many of the C++ programmers agree with him. The name definitely is not catchy, but don't let that put you off because he also said that this was his best idea. Even if you forget what the letters stand for, remember the principle. Objects own resource, constructors acquire them, destructors release them, and that's it. You will see this pattern everywhere in C++ standard library. Now let's apply RAII specifically to dynamic memory. The rule stays exactly the same. When an object is created, it acquires the memory. When an object is destroyed, it releases that memory automatically. The problem is that we don't want to write a custom class every single time we allocate something on the heap. Imagine writing your own constructor and destructor for every pointer you ever create. That would become repetitive very quickly. Fortunately, the standard library already provides classes that do exactly this. These classes behave like pointers, but unlike raw pointers, they automatically release memory when they are destroyed. Those classes are called smart pointers. They are simply RAII applied to dynamic memory. So what exactly is a smart pointer? Smart pointer is an object. That's the first important point. It's not just a special kind of raw pointer, it's a class. Inside that class is a raw pointer to dynamically allocated memory. The smart pointer takes ownership of that memory. You still use it almost like a normal pointer. You can access the object through it. You can dereference it. But there's one huge difference. When the smart pointer goes out of scope, its destructor automatically releases the memory. There's no manual delete and there's nothing to remember. The cleanup happens automatically because the smart pointer itself follows the RAII principle. Now let's check out the smart pointers themselves. The C++ standard library gives us 3 different smart pointers. Each one solves a different ownership problem. The first is standard unique pointer. As the name suggests, it has unique ownership. Only one smart pointer owns the object at any moment. The second is shared pointer. So in shared pointer, what happens is sometimes several parts of a program genuinely needs to own the same object. A shared pointer makes that possible by sharing the ownership. The third is weak pointer. It's a little bit different. It doesn't own the object at all. Instead, it simply observes an object that's managed by a shared pointer. We will see all of them later why that's useful. If you're wondering which one you should use by default, the answer is almost always the standard unique pointer. Only move to shared pointer if you really need shared ownership, and only use weak pointer when you specifically need a non-owning reference. So let's begin with the simplest and the most common smart pointer. A standard unique pointer has exclusive ownership of an object. The exclusivity is the important thing. At any point in time, only one unique pointer owns that single piece of memory. Because of that, copying isn't allowed. Think about what copying would mean. If we copied a unique pointer, we would suddenly have two objects claiming they both own the same memory. Then both destructors would eventually try to delete it. That would be a disaster. So, C++ simply prevents copying altogether. Instead, ownership can be moved. When ownership moves, the original unique pointer gives up the resource completely, and another unique pointer becomes the new owner. A unique pointer can move, but it cannot be copied. Because of its simplicity and efficiency, unique pointer should usually be your first choice whenever one object clearly owns another. Now let's stop talking about it and actually use one. So here let's open up example1.cpp and include IOStream. Then for our standard unique pointer and standard make unique, we would need memory. And let's include string just for our purposes. Now let's create a class named book. Let's define our constructor, which is book, constant, standard string, title, and then we will standard cout that book created, and let's provide the title and then standard end line. This book constructor runs immediately when the object is created. Now let's create our destructor. Here we will standard cout that book destroyed, and we will provide the title and end line. And let's just create another function, void read. Here we will just standard cout that we are reading the book. So it's just a normal member function, and then we will privately declare the title. Now in the main, we will create a unique pointer that owns the book, and here standard make unique allocates memory and returns our unique pointer of a C++ programming book. Here notice that we didn't write the new keyword ourselves. We just wrote that it's a unique pointer. Now we use the smart pointer almost exactly like a raw pointer. So book, read, and standard cout, leaving main function. Now here, who's going to destroy the book? The answer is the unique pointer destructor. As the main ends, the book goes out of scope, so its destructor automatically deletes the book. Here, the book will go out of scope and the destructor automatically will delete the book. We never called delete, we never wrote any cleanup code. The book object was destroyed automatically because the unique pointer itself went out of scope. That's an RAII action. The lifetime of the memory is tied directly to the lifetime of the owning object. In modern C++, whenever you simply want a unique pointer to own a newly created object, make unique is usually the right choice. So now let's run it. So yeah, everything works. Standard unique pointer works wonderfully when there's one clear owner. But sometimes life isn't that simple. Imagine a library system. A book object might be used by the catalog, a recommendation engine, and a reading history at the same time. So who owns it? There isn't always a single answer. So that's where we use shared pointers. A shared pointer allows shared ownership. Multiple smart pointers can point to exactly the same object. Instead of deleting the object when one pointer disappears, a shared pointer keeps track of how many owners currently exist. This is called a reference count. Whenever a new shared pointer is created from an existing one, the count increases. Whenever one of them is destroyed, the count decreases. Only when that count reaches 0 is the object actually gets destroyed. That's a very powerful feature, but it also comes with a cost. Every copy updates the reference count. That means extra work compared to a unique pointer. So here's a good rule to remember. Use unique pointer by default. Only choose shared pointer when multiple objects genuinely need to own the same resource. Let's see what that looks like. So here in our example, we have memory, we have IO stream, we have our book constructor here, we have our book destructor here, our main function will change here. So here, instead of standard unique pointer, we will create a shared pointer. So this one will be the first owner. So here, let's get book 1 and we will use make shared, and once again our book will be C++ programming. Now let's standard C out owners book1.useCount and standard endline. At this point, only one shared pointer owns the object. Now, let's create a second owner by copying. So here, another standard shared pointer. We will use book2, but instead of making a shared pointer like this using standard make shared, we will just copy it. And then we will standard C out the owners and we will use count and standard endline. We will check the reference count from there and then we will read from book 2. Now our book 2 will go out of scope since there's another curly bracket and I'm closing the curly bracket here. And then let's check how many owners are there. And now we will write that we are going to exit the main function. So notice when this prints and this gets printed. Here in our previous function, we have seen that after exiting the main function, the book got destroyed. We will see the same thing here again. So now let's run it. Please notice what happened. We copied the smart pointer, but we did not copy the book. Both smart pointers referred to exactly the same object. The object stayed alive until the last owner disappeared. Here, our book got created only once, and the object stayed alive until the last owner destroyed it. We copied the smart pointer, but we did not copy the book. That's why our constructor was called only once. Both smart pointers refer to exactly the same object. Here we checked how many owners are there, and we checked how many owners are there as well from here. So at first we got 1, and inside these curly braces we got 2 owners there. Then we read the book, and after leaving those curly braces, we are getting that there's only 1 owner. But after that, when exiting the main function, there's another set of curly braces. So there we can see that our book got finally destroyed. Now we arrive at the third smart pointer. A standard weak pointer does not own the object. And mainly that's where the confusion starts. What's the point of a pointer if it doesn't own anything at all? It simply observes an object that's managed by a shared pointer. Because it isn't an owner, creating a weak pointer does not increase the reference count. That means a weak pointer doesn't keep the object alive. If every shared pointer disappears, the object is destroyed, even if several weak pointers still exist. Before using a weak pointer, we first have to check whether the object still exists. We do that by converting it into a shared pointer using the lock member function. If the object has already been destroyed, lock gives us an empty smart pointer instead. The important thing to remember today is much simpler. A weak pointer only observes. It doesn't own anything. So let's see that in action. Here in our same example, we have the book constructor, the destructor, and the read function. Here, let's clear everything and start again. Let's create the real owner, standard shared pointer, book. Here's our owner, and then make shared book, which is a C++ programming book. Now the weak pointer observes the object. It doesn't increase the reference count. So let's check that out. A weak pointer book, and it's gonna be an observer, which will observe the owner. Here, let's standard cout to check the user count. So owner use count, we will check that there. And before using a weak pointer, we call lock. If the object still exists, the lock returns a shared pointer. So if our standard shared pointer book gets something from the observer lock, only then it will go inside this if block where it will just read from the shared observer. Now we will reset the owner, which will release the ownership from the book. The shared pointer will release the ownership. No owners will remain, so the book will get destroyed. Now let's check if the observer lock is still there. So standard cout observer still has access to the book, else it will print that observer no longer has access to the book. And this one is the expected output. The weak pointer knows the object no longer exists. Then we will return 0. Now let's run it. So let's see what's happening. The book got created. Owner use count is 1. Then we read the book from here because from observer log we got a shared pointer back. Then we reset the owner. Since the owner.reset was called, the book got destroyed, and then we will call the observer log once again, and there it will return nothing. So the 0 or false will trigger this one, and this block will execute, which will say observer no longer has access. So there you go. That's the RAII mindset. And it's the approach you will see throughout modern C++ code bases. Thank you for going through the lecture with me. I hope we learned something together. See you in the next one. Bye-bye.